Good morning, everyone. Good morning. Hope all is well and everything's
Morning.
all right. Hey, how's it going? All right. So is everybody in? Like a few people still trying to connect. So hope you had a great weekend. Hope everybody's ready to get this week started. Let's see. We anybody have any general questions or concerns before we get going?
Mr. Tucker, I had a question.
Mm-hmm.
So I'm like finishing up chapter one with like the homework and the test and everything.
Mm-hmm.
Um, is the test the same as the homework? Is like it'll give you an example or no?
Oh no, that's the one of the main differences from the test to the homework. In comparison to the two. The homework, I mean, the test is really set up like a test, you know what I mean? So there are no help buttons, and you get the one shot because it's like supposed to be like, the simulated and actual test. Yeah. So since I'm not taking your notes away from you, it would be to your benefit to take some good notes going into the test and have them laid out there in front of you.
Okay,
All right.
that was
And
all I had.
also,
Thank you.
okay, good. Not a problem. And also take a look at the test review because it's very similar and it's set up in
Okay,
in a very similar way, and that'll give you an idea of what the test is going to look like, and that'll pretty much set you up for what you need to have in front of you for the actual test.
okay, that sounds good. Thank you.
Yep, no problem. All right, anything else, anybody else before we get rolling? Everybody good? Oh, hitting the wrong button. Hold on, guys. Here we go. So we left off. Yes. Okay, we're looking at 2.5 today. Yep. All right, so 2.5, transformational functions. And so we have 6 basic functions that we're going to look at in this section. And so most of this, well, not most of this whole section is all about graphing and everything. So um, I don't spend much time on it because really all you have to do is get a graphing tool, whether it be using your graphing calculator or, if you were to Google graphing tool, you can always use something like Desmos or whatever and type in the function and then get the graph. So just talking about the shifts in your functions. Notice our general, these are our basic functions here. Where did my pen go? There we go. So here's our basic linear function, going through the origin, basic parabola going through the origin, our cubic function right here. This is a square root, cube root, and then the absolute value mix of v. So the summary of those transitions and those shifts is on page 291. It should be 291. Unless they changed something, but it shouldn't have changed. But it's in that section. Scroll up past the first 3. All right. So basically what's going to happen in this section, they're going to emphasize the difference between the other one. These 4 scenarios. You have your basic function right here, x squared. And then so you will see what's the difference between having +1 inside of the x squared versus +1 on the outside of the square, or -1 inside of the square versus having -1 outside of the square. And so that's what this section is about. So if you have any questions on any of those transitions, those transformations, then let me know. But basically it comes from you exploring, looking at this summary chart here on page 291, and then exploring the transformations by plugging them into a graphing tool. Because we're not actually asking you. Now, if we were asking you to graph them by hand, then it would be something for us to, dig into, but we're actually asking you to graph it by a graphing tool. So if you have any problem finding something, then, let me know. But like I said, if you can either use, one of those graphing calculators like the TIs. I think Casio has one as well, a few of them out there. Or just Google graphing tools or graphing calculators. There are a bunch of free ones out there. Like I said, Desmos is one of them. All right. Questions on anything I've said? Let's scroll up. Good. All right, so 2.6 is combinations of functions and composite functions. All right, so the first exercise in this section is finding the domain. And we talked about finding the domain before. We're looking for all the values that can be used for X. Or in other words, all the values that can be plugged into the equation for X. And so that means to find the values that can be used, we would look for the values that cannot be used. All right, scrolling up some. All right, so the directions would be find the domain of each. First one they give is f of x is equal to x squared minus 7x. So we want to ask ourselves the question, is there a value that can be plugged in for x that will make the equation undefined? So whenever, in other words, that values that we cannot use, going back to that statement, we're looking for values that we cannot use. So is there something I can plug into the equation to make it undefined? Now for this one, we have x squared minus 7x. X squared is the parabola. So for this one, there is not a value that you can plug in for x that will make it undefined. There's nothing I can plug in there that get a situation that that I cannot use the value. I can plug in 0 because then I'll have 0 minus 0, which is a 0. 0 is fine. That's a legitimate number. So the domain for this would be negative infinity to infinity because I can use all values. And the next one, you'll see what we mean by not having a value that we cannot use. But in this case, there's nothing that will make this function undefined. There's nothing I can plug in to make it undefined, so I can use all values. All right, scroll up. So the next one, g of x, we have 2 over x minus 5. All right. So we have a rational expression here, or in other words, a fraction. Well, those are the same thing, rational expression, fraction. So once again, is there a value that will make this fraction undefined? Now we know whenever we have fractions, you see that I put it up here already. Okay, yeah, I put it right there. Can I make this fraction undefined? Whenever we have fractions, fractions can be undefined whenever there's a 0 in the denominator. So 0 in your denominator is undefined. So you have to ask yourself, what value will make me have 0 in my denominator? So see here, we will set the denominator equal to 0 and then solve it. So our denominator is x minus 5. Solve for x, that gives me x equal to 5. And the x equal to 5 is the value that I cannot use, because that's the value where you plug it in there, I get 5 minus 5 in my denominator, which is 0. So that's the value that I cannot use. And so you notice what my domain is. It's negative infinity to 5, then 5 to positive infinity. Don't forget those parentheses up against 5 means I can get as close to 5 as I want, but I cannot use 5. So 5 is not a part of the domain. Just saying I can get as close to it as I want to, just cannot use it. All right. Any problems? Any problems? All right, so h of x, we have 3x plus 2 over x squared minus 2x minus 3. So once again, we have a fraction. We have this rational expression, so we're going to set the denominator equal to 0. Solve it. So everybody doing that last problem. All right, so x squared minus 2x minus 3 equals 0. Go ahead and factor that out. Or if you wanted to use your quadratic formula, you could do that. Either way, you will get x equal to 3 and x equal to negative 1. Once again, these are the values that we cannot use. These are the values that will give us 0 in our denominator. And so our domain will look like this. So notice that we have 3 different intervals. If I look at my generic number line here, we come from negative infinity to 1, 1 to negative 1 to 3, and then 3 to positive infinity. And so that's what's represented here. Once again, parentheses on -1 and 3 just means I can get as close to -1 and 3 as possible, but I cannot use either one of those numbers. All right, any questions? Got one more. All right, last one like this. We have a radical. Got j of x is equal to the square root of 3x plus 12. You know, we call what's under the radical the radicand. So once again, we're asking the question, can you make the expression undefined, or when is this radical undefined? All right. So the answer to that is you cannot take the square root of a negative number. And we talked about taking the square root of a negative is us imaginary. So we don't want to go there with this domain. If it's turned imaginary, same thing as being undefined as far as our domain is concerned. So we cannot take the square root of a negative. So we want to set our radicand, what's under the radical, greater than or equal to 0. Because remember, it's okay to take the square root of 0. Square root of 0 is 0. So that's fine. So we want to know when is our radicand greater than or equal to 0. Because if it's less than 0, that means it's negative, cannot take the square root of a negative. So that's why we're doing greater than or equal to 0. So you always take what's under the radical, set it greater than or equal to 0. All right, subtracting 12 divided by 3 gives us x is greater than or equal to -4. So that means my domain is -4 to infinity. And notice because we had the or equal to, it's the brackets on the bracket on the -4. Infinity, always take your parentheses. All right, questions, any questions? All right, scroll up. All right, so here we have some shorthand symbols that will let us know what to do with our functions when we see them. So you got f plus g of x, which is f of x plus g of x. Just tells you to add those two functions together. F minus g of x tells you to subtract them. F times g of x tells you to multiply them. And f over g of x tells you to divide them. So just shorthand notation to tell you what to do with functions when you have them. Excuse me. All right, let's scroll up. All right, so notice they do define g of x and f of x first. So you're not expected to come up with f of x and g of x. They do define them for you. So here they give us 2x minus 1 is f of x, x squared plus x minus 2 is g of x. Ask us to find each. So the first one they ask us to find is f plus g of x. So that just means you're going to take f of x added to g of x. And that's what I have here. And then we combine our like terms. That'll be that final expression, x squared plus 3x minus 3. Same thing with f minus g of x. All right, so don't forget to subtract. When you're doing subtracting your polynomial, you distribute that negative. It's 2x minus 1, then minus x squared minus x plus 2. Then combine your like terms once again. That'll be negative x squared plus x plus 1. Mhm. F times g of x. We're going to multiply them together. So that's 2x times x squared, 2x times x, 2x times negative 2. And negative 1 times x squared x plus x and negative 2. So it gives me this expression down here. Then from there, combine your like terms. 2x squared minus x squared is 1x squared, negative 4x, and negative 1x would be negative 5x. Questions? Any questions? Last one like this. F of x over g of x. It's 2x minus 1 over x squared plus x minus 2. And then you would explore it to see if it's possible to reduce it any. And we can't in this case. There's nothing to reduce, nothing to factor. So that would be the answer.
Mr. Tucker, you can't factor the bottom of it?
Let's see if you can. That's 2. You can factor the bottom, but it wouldn't help because nothing can cancel out with the top.
Oh, okay.
So, yeah. Good question. Good question. Any problems with anything that's been said up to this point? Make sure we're good. Oh, one more. I think somebody asked what this might be why I haven't read. Okay, one more, just in case. Let's say if they would have f over g of 2. So notice this time they substituted in 2 for x. So all that means is you put 2 wherever you see x in this expression. We already determined that that was f of g of x. So if you need to find f of g of 2, then you plug 2 in where you see x. And so that's what I did here. So that's why you have 2 times 2 minus 1, 2 squared plus 2 minus 2. Once again, we put in 2 everywhere we saw x. And so that'll be 4 minus 1 over 4 plus 2 minus 2, and ultimately give us 3 over 4. Any questions? All right. Composition of functions. We used to call it fog of x and golf of x. We have this circle. It's not really the letter O, but it's a circle. And you know, when you see it, when you actually look at your notation, they ask you to do it. It's a little different than what you normally see. It's just a circle in between f and g. And all that means is that I'm going to take this g function and plug it into f. Or if it's golf of x, that means I'm going to take the f and plug it into g. So whatever is the second function, you're going to take that one and plug it into the first function. That's not okay. In the wrong way. There we go. So that's what this notation means. You're just taking that one function, the second function, and plugging it into the first function. All right. So once again, they give us f of x and g of x. We have 3x minus 4 and x squared minus 2x plus 6. And we want to find fog of x. So once again, we're going to take the second function, plug it into the first function. So we're going to take g of x and plug it into f of x where we see x. And so that's what I did down here. We had 3x minus 4, so now we have 3 times x squared minus 2x plus 6 minus 4. So the minus 4 is still back there. Distribute that 3. That's 3x squared minus 6x plus 18 minus 4. Then combine your like terms of 18 and 4. So 18 minus 4 will be 14. All right. The next one is the other way around, golf of x. Once again, we're taking the second one and plugging it in to the first one. So we're taking f and plugging it into g, where we see x. So that means you have to plug it into two places here. So that's what was done right here. So that's 3x minus 4 squared, then negative 2 times 3x minus 4, and then plus 6. Make sure we're okay with this substitution. All right. So in the purple is the expansion of 3x minus 4 times 3x minus 4. So I just went ahead and FOIL that out. So don't forget, you can't just square 3x and square 4. You have to expand that out. 3x minus 4 times 3x minus 4. So if you FOIL that out, get 9x squared minus 12x plus 16. And then combine your like terms, that'll give you 9x squared minus 24 plus 16. And then distribute negative 2. And that'll give you negative 6 plus 8. And then you still had a plus 6 at the end of that. Combine your like terms, that'll be 9x squared minus 30x plus 30. All right, any questions? Look at the next one. All right, so for this last one, dealing with these type of scenarios or situations, they give us golf of 1. So just like before, when you substitute in a number for x, that means you're going to plug in that number for x. So it's two ways that we can handle this problem, especially since we've already found the generic way of expressing golf of x. First way is to keep one in it and then just do the pieces. So remember, golf of x means you're taking f of x and plugging it into g of x. But if I know what the x is, which is 1, I can plug 1 into f. And that's what I did right here. So remember our function f was 3x minus 1 minus 4. So you plug in 1, that's 3 times 1, which is 3. 3 minus 4 is negative 1. So once you have that value, then plug it into g. And that'll give you 9. Negative 1 squared minus 2 times negative 1 plus 6. 1 plus 2 plus 6 is 9. So that's one way of doing it. The other way is, since I already have this, 9x squared minus 30x plus 30, I can just plug 1 into that. And so that's what I did right here. And you see that either way, you still get 9. So 9 times 1 squared minus 30 times 1 plus 30. 9 minus 30 plus 30 gives you 9. So once again, either way you get 9, doesn't matter which way you decide to do it. Any problems? Any problems? Very good. All right, so that's it for 2-6. This time he was just emphasizing what I already said, that the second one goes into the first one. So I think somebody else had asked that. All right, let's see what 2-7 has in it. Inverse functions. I don't want to do that today. So that's 2-8. I want to do both of those. Do I want to do one of these today? Very short. Yeah, let's start this and get to a good place to stop. Yeah, we'll go to the horizontal line test. Yep, let's do that. Okay, let's start 2-7 and then stop about halfway through. All right, so 2-7 is the talks about inverse functions. So we're gonna let f and g be two functions such that when you take g and plug it into f, it simplifies to x. And then when you take f and plug it into g, it also simplifies to x. Now, both of them have to occur. Both of them have to occur. So that means you're gonna have to test both of them. There will be problems wherein one of them, when you plug g into f, it'll simplify to x. But then the other one, when you plug f into g, it won't simplify as x. And so that means they're not inverse functions. So both of them have to occur. So you do have to check both of them. So if this occurs, then g is the inverse function of f. And the notation for that is what we have right here. You have f with a -1 superscript, kind of like an exponent. And so the way you read that is f inverse of x. All right.
Mr. Tucker, I'm sorry. Can you scroll up just a little bit? Okay, yeah. I just needed to see what that top word was. Okay.
Oh, okay. Yep.
Thank you.
Not a problem. Anybody else want to scroll up some? Everybody good? Oh yeah, then that last statement about it. The domain of f is the range of your f inverse and vice versa. So your domain and your range will switch for both of them. Mhm. Everybody done with the black? All right, so first exercise asks us to show that the functions are inverses of each other. So we'll take G. It doesn't matter which one you decide to do first. I'm going to go ahead. I took G and plugged it into F first, then we'll take F and plug it into G. Remember, if they're inverses of each other, it should simplify down to just X. So plugging in X minus 2 over 3 for X. Notice the first thing that happens is that the 3's cancel. And then that'll leave us with X minus 2 plus 2. And then the 2's cancel, leaving us with just X. All right, is everybody okay? So now we got to take 3X plus 2, plug it in for X in G. That's what I did down here. So that's 3X plus 2. I'm gonna just put the parentheses there just to signify what I plugged in. Nothing is holding those parentheses there. So 2 minus 2 cancels. That leaves you with 3X over 3, and then 3 over 3 cancels. So that leaves us with X. Any problems? Any problems? All right, so one-to-one functions. If each element in the domain goes to exactly one element in the range and vice versa. All right, so if the function is not one-to-one, then it does not have an inverse. So that's the reason why we want to know if our function is one-to-one. The function is not one-to-one, it does not have an inverse. So remember, we're not just talking about functions. Remember, functions, our domain could go to more than one. Our domain couldn't go to more than one value, but our range could. So the range could repeat. In this case, one-to-one means that there are no repeated values. So what we would do is use the horizontal line test to determine whether our function is one-to-one or not. And remember, like I said, what's important about knowing if your function is one-to-one or not. If the function is not one-to-one, it does not have an inverse. So if you remember the vertical line test, it's the same thought process, same principle, except we have a horizontal line. So if a horizontal line crosses or touches the graph more than once, then it's not one-to-one. So now it can still be a regular function, it's just not a one-to-one function. By doing that red sentence. Okay. So here, horizontal line test, my regular linear equation is 1-to-1. Horizontal line only going to touch it once, no matter where you draw it. Your parabola, though, parabola is not 1-to-1. Now, notice in the purple, I said it is still a function, but it's just not a 1-to-1 function. Okay. Draw a horizontal line through your parabola. It's going to touch it twice. So that means it's not a 1-to-1 function. Then our cubic equation here is 1-to-1. No matter where you draw your horizontal line, it's only going to touch it once. Any questions? Any questions? All right. Any general questions before we look to close out today? Anybody try anything? Any problems? Got stuck on anything? Or are we good right now? Anybody? Okay, so we'll pause right here. I didn't want to get into the next part of this and then have to stop like right in the middle of lecture or whatever. So I think this is a good place to pause. And our next class, we'll close out 2.7 and then finish off 2.8. And then we'll talk about how we're going to move from there because we'll actually be done with chapter 2. All right. So if you guys are good, I am good. I will see you on next class. Be safe.
Thank you, Mr. Tucker. Have a good day.
Thanks.
Have
You
a
do the
nice
same.
one.
Take care.
Have a good day.
A good one.
Thanks. You do the same.